So
Did you really?
probably.
And that would be the end of this.
Yeah. So hopefully you got through and found that a lot of the problems in 5.1 they're a little bit on the tedious side. I mean, you're slicing things up, you're making little rectangular areas, you're finding the area of each one of those and then adding them up and coming up with some approximation for the area between the curve and the horizontal axis. There are some problems at the end that are more like the more complex things that we did. But without doing that, I mean, really, there wouldn't be any hope of figuring out those really complex ones. And then we've really laid a lot of the groundwork for understanding 5.2. We're going to take 2 days to do this section. And hopefully, because it builds right on top of that more complicated stuff that we did in 5.1, it's going to make this a little bit easier. Not that this is going to get ridiculously complicated. We're going to still stick with that basic rectangular slicing and summing method. And hopefully it's not too bad. Okay? All right. So let's take a look at the starter questions here, and then we'll do this problem that's a little bit different than what we dealt with last time. So it says, can area ever be negative? So if we're generally talking area, can area ever be negative? Okay? The answer there is nope, usually can't. Okay? Because we're taking a positive length for a width and a positive length for a height and multiplying those together, and we're getting a positive quantity. Okay? What's the formula for the area of a trapezoid? So the formula for the area of a trapezoid, remember we talked about this shape last week, but we said the formula was a bit more complicated. It's going to be 1/2 b1 plus b2 times h is what it is. So it's a fair amount more complicated than just figuring out the area of a rectangle. And then if you'll recall, which one was the most accurate approximation if we were doing rectangular approximation using the left end point, right end point, or midpoint? Which one was the most accurate? Okay, the midpoint was most accurate. Can anybody describe to us why?
Does the right or left are either too high or too low, but the mid is right in there?
Okay, it's kind of right in the middle. I'll buy that. Okay, here's what I think would be kind of a little bit more descriptive way of describing that same type of thing. The midpoint, oops, spell this correctly, midpoint takes into account what's happening on left and right end. It's usually less extreme. It kind of balances out. I mean, if we've got an increasing function and the left end point is on the low side and the right end point is on the high side, the midpoint's probably going to be somewhere in the middle. Not perfectly in the middle, but it kind of compensates for those two extremes. Okay? That's usually why that's a little bit more accurate. Why didn't we use that more often? Yeah, the equation for a midpoint is a little bit more complicated. Now, if all you have to do is on some of your problems, if all you had to do is just eyeball where the midpoint was, on the example that we did from 0 to 3, and we did 3 subintervals, it's pretty easy to find the midpoint between 0 and 1, 1 and 2, 2 and 3, and just say, well, it's 1/2, 3/2, and 5/2. If we had to do that for 500 intervals, then it would become a bit of a pain in the butt, okay? Whereas the formula for the right end point was relatively easy to work with. Left end point, slightly more complicated, but we usually stick with the easy one, okay? So we are going to do a midpoint approximation, and I'll show you that on this problem right here. It says, so in the last section, every single function that we dealt with on every interval where we were interested in approximating the area, they were all positive functions, and we were always kind of accumulating the area as we go from left to right. Okay. Well, it's possible to have a function that has negative function values, so let's think about how we deal with that. So we've got this function f of x equals negative x squared plus 2x. The interval is from 0 to 4, closed interval from 0 to 4. It says find an approximation for the area between the curve and the x-axis with a Riemann sum like this. And remember what this means. We're going to sum up from the first rectangle to the nth rectangle. This right here is a height, and this right here is a width. And it says very specifically, use 4 equal subintervals, and it says let xi bar, okay, there's that little bar across there, and I think we've talked about that in this class. Whenever you see the word bar, it kind of means average, okay? So this is going to be the midpoint of the ith subinterval. So we are going to use a midpoint approximation for this. So remember, it says x bar I is the midpoint, and here's the formula. And what I want you to take note of, if you look in the textbook doesn't use this formula. If we're going to do this kind of systemized and formula driven, this is a much better one to use. So again, we start with the left end point. We go forward one full delta x, and then we back up half a delta x. That puts us in the middle of that interval. Now on this particular one, we can actually eyeball it. It's really not that hard to eyeball it. So let's go ahead and do that. But we are going to see this crop up a little bit later on. So let's put that one right there, right here, and right here. So there are our midpoints. Now the midpoint on this one is 1/2, 3/2. This would be 5/2, and this one right here is going to be 7/2. Okay, so 3.5. So I'm going to make this just a little bit bigger so we can deal with it a little better. Okay. So let's draw our little rectangles. Okay, now I'm going to need a little bit of help calculating these, so if you double check our calculations. Remember, we're going to sum from I equals 1 to 4, because we've got 4 subintervals, and then we're going to have a function height. So this particular one is a little bit more complicated than the ones that we dealt with last time. It's going to be negative x bar I, quantity squared, plus 2 times x bar I, and then we multiply it by the width. Now, on this particular one, this interval goes from 0 to 4, and if we make these equal subintervals, remember it's b minus a, so 4 minus 0 over 4, so we get lucky on this one. The delta x, the width of each one of these subintervals, is 1, and we're doing that for convenience sake to make these a little bit easier to understand as we start out. Okay, any questions? Okay, so let's see what we get here. The first, so this is going to be x1, x bar 1. This is going to be x bar 2. This is x bar 3, and this is x bar 4. There's the midpoint of each of those 4 subintervals. Okay, so when I plug this first one in, here's what I'm going to get. I'm going to get, let's see, this is going to be negative 1/2 quantity squared plus 2 times 1/2. And then we're going to times that by. Now, I don't really need to write the 1, but what I'm going to do is I'm going to pull the 1 out front, and I'm going to write a big set of brackets, and then let's write down. So we're pulling out the width like we did last time, and then I'll just compute the function height, if that's okay. Everybody good there? Okay, so here's the next one. The next one would be what I get when I plug in the midpoint of the second subinterval, x bar 2. So this is going to be negative 3/2 quantity squared plus 2 times 3/2. I'll put that in parentheses just for the sake of it. Okay. And so again, don't lose track of literally what we're doing here, because the summations in these formulas kind of drive the work, but it has a geometric interpretation. I'm computing the function value right here, and then I'm drawing a little rectangle. Now, just for the heck of it, let's figure out, this looks like it's a little bit more than 1/2 a unit tall. Let's just double check. This would be minus 1/4. This would be plus 1. So this is 1 times, this is 3/4. Okay? The area of that little rectangle is 3/4. Okay? If I eyeball this one just because of symmetry, let's check this guy right here. So this is going to be negative 9/4, and then this is going to be plus 3. So in fourths, that would be 12/4 minus 9/4. So this second one is also 3/4. You with me there? Okay, now again, we're just blindly going through here, and we're doing this math. So the next one would be negative 5/2 quantity squared, negative out front, of course, and then plus 2 times 5/2. And then this last one would be negative 7/2 quantity squared minus, or excuse me, plus 7/2. Everybody good there? Okay, so let's see, negative 25 fourths plus 5. In fourths, that's going to be 20 fourths. So I've got negative 25 fourths plus 20 fourths. So this is going to be negative 5 fourths. Is that okay? And then this one right here, this is going to be negative 49 fourths. This is going to be plus 7. So in fourths, that's going to be 28 fourths. Am I right? So 49 fourths, negative 49 fourths plus 28 fourths, that's going to be negative 21 fourths. So these are all the function heights. So let's draw this one right here. This says negative 5 fourths, and let's see if that looks about right. I mean, if you eyeball that, that looks pretty good. So here's our rectangle right there. And then negative 21 fourths, that looks like about negative 5 1/4. Let's just eyeball that. Let's come straight down here. And I'd say about right there. That looks a little bit lower, but we're just eyeballing it, so we'll go with that right there. There are the rectangles that we would draw for the, using the exact same method that we worked on last time. Okay?
Doesn't seem that accurate.
Doesn't seem that accurate? Okay. Well, let's add these up and let's see what we get. So this ends up being, this is 6 fourths minus 5 fourths. So that's going to be plus 1/4. And then minus 21 fourths. So altogether, this is going to be negative 20 fourths, which is negative 5. Okay, now, every one of these, so this is how we kind of systematized it. We had pulled that one out front, but every one of these, if I represented this, that first rectangle was 3/4 for a height, 1 for a width. That next rectangle was 3/4 for a height, 1 for a width. This next rectangle was negative 5/4 for a height, 1 for a width. And that last rectangle was negative 21/4 for a height and 1 for a width. And if I add all those up, I get this answer right here. Now, if we're trying to find the area between curves, there are a couple things that go wrong here. How can that possibly represent the area between a curve and the horizontal axis? If we're talking area, is there any way that's right? It's not right, okay? Weston, it is pretty darn accurate, okay? But we need to talk about a couple of things first.
Accurate.
Okay. So,
Confused.
we want to think about it this way. We're going to introduce a little bit of vocabulary. So this problem illustrates the idea of signed area. No, this area right here is not negative 21/4. When you take that height, which is negative 21/4, and multiply it by the width, the area is not negative 21/4. But that negative 21/4 does represent something, and we'll call that the negative sign, or the signed area, which in this case happens to be negative. So here's what you want to keep in mind. We're adding things up as we go from 0 to 4. In other words, we're adding things up in the positive direction. Okay? So we're going from the left to the right. We're moving in a positive direction. And as we move in a positive direction, when we were working with this last time, all of the function heights were positive, so we didn't have any worries about, hey, what type of area am I accumulating? It was all above the x-axis. It made sense that it was all positive area. Okay? So the area above the x-axis counts as positive area. Well, if we continue with this, there's nothing wrong with what we did. We just need to figure out how to deal with this. If this has a negative height, what we do is we calculate the area. We kind of strip off the negative. Okay, so this right here would be 5/4 as far as the height goes. How far is it from top to bottom here? It's 5/4. How wide is it? 1. Multiply those two together. The actual area of this is 5/4, but we need to treat it differently because it's below the x-axis. Remember, what we're dealing with here is how these things are accumulating. Certainly, this accumulates things below the x-axis differently than it's going to accumulate things above the x-axis. Think in terms of velocities. Think of what positive velocities would accumulate and think about what negative velocities would accumulate. There's got to be some direction that comes into play here. So any area above the x-axis is going to count as positive as we move from left to right, and anything below the x-axis counts as negative area. Whoops, if I can spell right. Okay? So what we call this the net area. So these two counted as positive areas, these two counted as negative areas, and when we put all of those together, we get what we call the net signed area, or just plain old net area. Now, if you look at this, just eyeball this, doesn't it look like we accumulated a little bit of positive signed area and a whole bunch of negative signed area? This goes way down here. This function value at the end is -8. That's a lot of negative signed area, isn't it? To kind of counterbalance what we accumulated there as positive signed area. Everybody okay with that? Okay, so as we're accumulating from left to right, as we move in the positive direction, anything above counts as positive, anything below counts as negative. Positive signed area above, negative signed area below, combine them together, that will give us our net area. So this is our net area in this problem right here, okay? So because this slicing and summing, this rectangular process comes up so often, we're going to come up with our own notation, and we're going to come up with a name for this. So this process of accumulating signed area is called integration. That second branch of calculus, we dealt with differential calculus, that second branch of calculus is what we call integral calculus, which is based on integration. So there's this ugly definition in here, and I want to zoom in on this, and let's talk about what these parts are, and then we'll figure out some interesting properties of this. So this gets very mathematical and very wordy, but it says if f is a function defined for a less than x less than b, and notice that it can be equal to those, it's basically saying f is defined on a closed interval from a to b. That's a little easier to understand, okay? Divide the closed interval into n subintervals of equal width, so a regular partition like we've been talking about. And then it says let x naught equal a and let xn equal b, and then all these other points in between are the end points of the subintervals, okay? And then we let x1 star, x2 star, and xn star be any sample point you want, any point where you want to find the function value. Now we've been pretty specific. We've done either left end point, right end point, or midpoint to evaluate the function to see how tall it is. This says you can pick any one you want. Okay? So it says x sub I star lies in the ith subinterval between x sub I minus 1 and x sub I. And then it says the definite integral of f from a to b can be represented like this. So let's talk about this funny little symbol right here. It's kind of a squiggly little s, kind of an elongated s. Yes, it's on the front of your math book there. That's called an integral sign. Okay, this number down at the bottom, or that's represented as a letter right now, okay, is called the lower limit of integration. This number up at the top, represented by the constant b right now, is the upper limit of integration. Okay, this thing right here, this function is called the integrand. And that dx right there, we call that the variable of integration. Now, I'm going to show you why they would have come up with this notation in just a second, but I want you to notice over here, it's got the limit as n approaches infinity, and then it's got sigma notation. This stuff should look familiar. We're adding things up, and what are we adding up? This is a height, and this is a width. So this is the same thing that we worked on last week. And if you'll notice, all they did is they said, you know what, rather than writing this ugly notation with f of xi star and delta x, let's call the height f of x, and let's call the width dx for delta x. Okay? So that's how those things are related. Okay, and then it says, if the limit exists, and it's the same value for all possible choices of the evaluation point, then we say that the function is integrable. Okay? That means it has a number answer that represents the signed area on that interval. Okay? So we want to notice a couple of things about this definition. Okay, the first thing is there's kind of a rationale for how this notation kind of came about. So we're used to this notation, this summation notation, this Greek letter S, and taking the limit as the number of slices goes to infinity. Hopefully that makes sense from our discussion last time. Well, rather than write down the limit and the n and the sigma notation and everything, they just said, you know what, let's just sum with a big capital S from A to B. Everybody knows we're going to make rectangular slices and add them up. Let's just use a big S for the slicing and summing process, and let's tell them where to start and tell them where to stop. Start at A, stop at B, and use this function right here. And these represent the height and the width of each one of those rectangles. And then we just get a little more lazy little s, so it doesn't look like a regular old s. And we're going to integrate. We're going to sum up the area from A to B, f of x dx. Again, this still represents the height, and that still represents the width. Okay? So that's the first thing. That's where the notation came from. That's kind of the rationale for how that would have been come about. Okay, the next thing is the definition uses equal subintervals. Okay? They did that for convenience. That makes it nice and easy, but that's not a requirement. You can break it up any way you want. You can make a couple wide ones, a bunch of narrow ones, and so forth. And we talked about this before. Since we're taking the limit of the summing process as the number of slices approaches infinity, even if you started with different widths, we're going to make so many of these little rectangles, so many of these little subintervals. How wide are they each going to end up being effectively? If I make an infinite number of rectangles from 0 to 3 or whatever, they're going to end up shrinking, so they're so tiny, the width is going to tend towards 0. Okay, so the width of all of these will approach 0. So it doesn't matter if they start with different widths. They're all going to approach the infinitely small width of 0. The same infinitely small width of 0. Okay, go ahead and flip the page over. There's some other things that we ought to be aware of, and then we'll actually do some problems and find some nice number answers. Okay, continuous functions on a closed interval are integrable. Continuous functions on a closed interval are integrable. So what that means is if you've got a continuous function on a closed interval, you can find a number answer that represents the net area between the curve and the horizontal axis. Okay? So there's a theorem in your textbook that takes this just a little bit further, and it says this. If it's continuous on a closed interval and it has only finite number of jumps, and I'll add or holes if you want, then it's still integrable. You can still find a number answer for it. So I'm going to take this example right here, and this is something that you've seen before but maybe haven't done a whole lot of. Okay? This is the floor function, or sometimes it's called the greatest integer function. It looks like this. Run along 0, open circle, hop up here to 1. Run along here. By the time you get to 2, open circle, hop up here right here, and then go like this. And it just continues to go in this stair-step fashion. Okay? So what we want on this one is we want the signed area for that function between 1 and 2. Signed area for that function between 1 and 2. So we're going to go from 1 to 2. Actually, yeah, let's go from 1 to 2. That won't be bad. So we're going to go from 1 to 2. So that's how we'd represent the signed area using an integral notation. So here's what we're going to do. I'm going to add up the area from here, to this end point right here. Now, if I do that, and I'm going to zoom in just a little bit, what I'm going to do is I'm going to take this and I'm going to slice this up. If I slice this up, okay, does everybody agree that for every single one of the rectangles, starting at 1 and going to just before 2, they've all got a width and they've all got a height? Okay, so really the only question is what happens right here. What happens at this last one? Well, how thin am I going to make that very last one? I'm going to make it infinitely small. So if I were to draw a little rectangle around this, like this right here, and exclude everything but that little one right there that has a hole at the top. The only one that has a hole at the top is right at 2, right? Even at 1.99999, it's still got a function height of 2. Sorry, 1. Okay? So, does everybody agree that the area of this box right here would be 1? Pretty much.
Yeah.
And if we took the limit as n goes to infinity, the number of slices goes to infinity, how wide is this little rectangle that we were concerned about?
Very useful.
Very, very small. In fact, infinitely small. So small that if we take the limit and add up all those little slices, is that last one going to make a difference? Not at all. Okay? So this limit from 1 to 2 would be 1. In fact, if I did the integral from 1 to 3 of the greatest integer function, okay, then I've got two concerns. I've got a concern on this endpoint, and I've got a concern right there. How wide does this little sliver right there in the center, how wide does it get if we take an infinite number of rectangles? Okay, it effectively turns into a 0. And that's why it says if I have a finite number of those, I can still add up. So this would be 1 and this would be 2, because the whole box is 1 unit wide and 2 units tall. This would end up being 3. Okay? Does that make sense? Okay. Seems a little bit weird, but think about it for a while. Okay, let me give you a different example. Okay, this is a weird function. Those of you that go on in math, you might run into this at some point. We've got this function where it's a piecewise function. Its value is 1 if the number we plug in is rational, and its value is 0 if the number we plug in is irrational. Now, there's a theorem that says in between every two irrational numbers, there is at least one irrational number. So take the number 5, 6, and the number 1. In between 5, 6, and 1, you can find an irrational number in there. Okay? Take the number 49 fiftieths and 51 fiftieths. In between those two numbers, there's got to be an irrational number. Okay? Now, we don't have time to prove that, but here's the idea. What will happen is when I pick 0, 0 is rational, so I get a 1. If I pick 1/10, I get a 1. But in between there's an irrational number, so there's going to be a 0. So what's going to happen is every time I pick a rational, it's up here. Every time I pick an irrational, it's down here. So what I end up with is something that just bounces back and forth. I've got a whole bunch of numbers at 1 and a whole bunch of numbers at 0. So let me draw a little rectangle right here. I can always find a point at the bottom, a point to evaluate an irrational number that gives me a height of 0. And I can always find one that gives me a 1 up at the top. So how do I decide how big that rectangle is? You can't, okay? Because this has an infinite number of discontinuities, it is so discontinuous, there's no way we can figure out what the area is. So the integral from 0 to 1 on that particular function does not exist because it is what I refer to as ridiculously discontinuous, okay? All it does is bounce back and forth. There's no way you could decide, okay, on this little sliver right here, I know the height is 1. Because if you use two rational numbers as endpoints, there's got to be an irrational one in between, and you could use that for the evaluation point, okay? All right, so kind of an interesting note there. So let's take a look at this next example. It says the integral from a to b f of x dx is a real number. It's a real number. It represents the net area, could be positive, could be negative, could even be 0, between the curve and the horizontal axis. A lot of times we always call it the x-axis. It doesn't have to be the x-axis, okay? And the net area depends on this. It depends only on the function that makes the shape, and the upper and lower limit. Because the upper and lower limit, they tell us where to start and where to stop adding. It does not depend on the variable we use. Okay, I think we talked before about dummy variables. It doesn't matter what variable we use. It's the function that makes the shape, and it's the starting and ending point, the upper and lower limit, that tell us where to start adding and where to stop adding. Okay? So all we need to do is just make sure that all the elements of this integral notation match up. So if I have this right here, this is my integrand. It's f of x. It is a function of x. That's going to represent the height. That dx needs to be a differential of x. I couldn't mix this with a y here and an x there, or an x here and a y there. Wouldn't work. This needs to be an upper limit for x and a lower limit for x. So we'll actually run across things like this. But if this is f of theta, everything else has to be in terms of theta. So probably like a trig function or something like that, although it wouldn't have to be. If this is in terms of u, everything else has to be in terms of u. The limits, upper and lower limits, have to be in terms of u, and the constant, the differential, has to be in terms of c. Okay? All right. So we're usually going to use a regular partition, nice equal subintervals, and we're usually going to use right endpoints just because that makes it nice and convenient. So theorem 4 in the textbook says, hey, if you want to compute this, you're going to use this limit. Again, we've dealt with this before. There's our height, there's our width, and we're going to sum up these n rectangles. We're going to use a regular partition, and we're going to use right endpoints. Okay? Any questions? Okay, so the cool part about this is if you were paying attention last week and thought about this a little bit over the weekend and looked at the homework and did the homework, this is not going to be any more difficult than what we dealt with there. Okay? So, again, midpoints are more accurate, but we're going to use the right endpoint just because that's going to be a little bit easier. So it says, express the limit as as n goes to infinity, the sum from 1 to n, negative x sub I squared plus 2 times x sub I delta x as a definite integral on the interval from 0 to 4. Then use the limit to find the net area between the curve and the x-axis. Does this look familiar? So, it's the one we did at the beginning, right? That's the function. So let's write it as an integral first. The integral is going to be, where do we start adding and where do we stop adding? Start at 0, stop at 4. What's the function that makes the shape and gives us our heights? Negative x squared plus 2x. And then we slap a dx on there. Now, if you want to put that in parentheses, there's certainly nothing wrong with that. But not putting them, I mean, everybody, when you start writing integrals, okay, when you slap a dx on the end, they know that everything that comes in between this symbol and the dx has to be the integrand that represents the function. Everybody okay with that? Okay, so let me slide this up so we can see what we've got here. This means it's going to be the limit as n approaches infinity, sum I equals 1 to n, and then I'm going to have a function value and a delta x right here. Set equal subintervals, right? Let's compute delta x. Delta x is b minus a, 4 minus 0. How many subintervals? N of them. So 4 over n. How do I write down my right endpoint? Sorry, yeah, right endpoint. I start with the left endpoint of the subinterval. So that's going to be a here, and this is b. So this is going to be 0 plus I times delta x, 4 over n. So the easiest way to write that is 4i over n. This should look really familiar at this point, right? Okay. So this is going to be negative 4i over n quantity squared plus 2 times 4i over n, and then times 4 over n. Any questions there? Here's my right endpoint. I'm plugging that in wherever there's an x, so that's why that's negative out front, 4i over n quantity squared, plus 2 times, here's my right endpoint, my x sub I, 4i over n times 4n. Okay, what is this right here? It's a height. And what is this right here? It's a width. Okay. Any questions? Okay. Let's clean this up just a little bit. Let's see, we're going to write 16I squared over n squared. Then I'm going to write plus 8I over n, and then I'm going to times that by 4 over n. Everybody good there? I'm going to distribute through, if that's okay. So this is going to be negative 64I squared over n cubed. And then this is going to be plus 32I over n squared. Everybody okay with that? Okay. Now, if you've got your notes handy from the last section, we're going to need those in just a second, because here's what I need to do. I need to find the limit as n approaches infinity of this expression right here. This will tell me what the answer is if I can find this limit. So let's see what we've got. We've got the summation I equals 1 to n, negative 64I squared over n cubed plus 32I over n squared. Now, with the summations, I can actually break these apart, can't I? So I'm going to break this apart into the limit as n approaches infinity, the sum from I equals 1 to n, negative 64I, whoops, that was a square, didn't I miss that? Tell me if I make a silly mistake like that. That's cubed, okay? And then plus the limit as n approaches infinity, sum I equals 1 to n, and this is going to be 32I over n squared. Everybody okay there? Did you get them all written down correctly? Make any mistakes? Okay, we're in good shape? Okay, so I'm going to rewrite one more time, and then we're going to have it in a format that we can really do some work here. So this is going to be the limit as n approaches infinity. Now, what's the only variable in the summation? In the summation. Isn't it I? N is a number that we determine out here. Okay? So this is going to be, I'm going to put a negative 64 over n cubed, and then I'm going to sum from I equals 1 to n, I squared. And I'm going to do the same thing on the other one, limit as n approaches infinity. I'm going to pull out a 32 over n squared, and then it's the sum from I equals 1 to n of just a plain old I. With me there? Okay, now I'm going to change colors for this. I'm going to do this one in red. So this is going to be, well, let's see, gosh, that's a, yeah, so we've got a limit as n approaches infinity, negative 64 over n cubed, and then I've got the sum from 1 to n of I squared. That's the sum of the first squared integers, right? First n squared integers. That's at the top of that second page, I think, in 5.1. Correct me if I'm wrong, but this sum right here, that sum right there is n plus 1, 2n plus 1, all over 6, isn't it?
That's right.
With me there? Okay. Now I'm going to change to green. I'm going to do this one in green. This is going to be plus the limit as n approaches infinity, 32 over n squared, and then this limit right here, or sorry, this sigma notation right here, this is the sum of the first n integers. And that formula, remember that little Carl Friedrich Gauss, he figured this out, n plus 1 all over 2. With me there? Lots and lots of tedious work, but this is going to pay off when you're in 1220. Okay. If I were to multiply these together on the top, okay, this would be the limit as n approaches infinity. I'd have a negative 64. I'd have, let's see what I'd have here. This would be 6n cubed here, And then I'd have, if I multiplied all these together, I'd have an n times an n times a 2n. So this would be 2n cubed plus a bunch of other stuff. My question for you is, do I have to figure out what this other stuff is? And why not? Dominant terms, right? What's the most dominant term on the top? 2n cubed. What's the most dominant term on the bottom? 6n cubed. So in the limit, only in the limit, those cancel off. So I end up with negative 64 over 3. Is that okay? Cancel the 2 with the 6. Good there? Okay. All right, so let's take care of this mess right here. Okay, this is going to be 32. We'll take the limit as n approaches infinity. 32, this is going to be n squared plus n, and this is going to be 2n squared. So in the limit, this is the most dominant term, and that's the most dominant term. So this is going to end up being, well, 32 times 1/2. Okay? So this is going to be negative 64 thirds plus 16. Am I right there? Okay. So in thirds, let's see what we've got here. Negative 64 thirds plus 48 thirds. So let's see, and that's a 4. So what do we get here? 16 thirds, and it's negative, which is negative 5 1/3. Okay, now we got to go back and think about what this means. What does that mean?
Our first approximation is 1/3 off.
That's the net area. That's the signed area that has accumulated on that function from 0 to 4. So if we slide back up here and take a look at this, the net area that would accumulate here would be negative 5 1/3. What was our guess? Using midpoints and only 4 subintervals. Negative 5. We were only 1/3 off, and we only used 4 equal subintervals. On this one, we used an infinite number of rectangles, and we ended up, this is the exact answer. Negative 16 thirds is the exact answer. And on a test, I'd much prefer this one right here. I just wrote that as a mixed number for comparison. Okay? Any questions? Okay, so here's the cool part. You have some problems that are like this. We can go through and we can go on one, at least one with polynomials, because they've got the squares and stuff like that we've got formulas for so we can add up the i's. We can go through and figure out answers for those. But we can also just set up expressions for the definite integral as a limit of sums. So we're going to sum from 2 to 5 on e to the x. In order to do this, we need to come up with the limit as n approaches infinity, the sum from I equals 1 to n, and then remember, we've got to have a height here, and we've got to have a width here. Well, what did we figure out first? Delta x. And how did we figure that out? B minus a, 5 minus 2 over n. So that's going to be 3 over n. And how did we figure out our evaluation point? Remember the right endpoint? A plus I times delta x. So that's going to be, what's a? 2 plus I times what's delta x? 3 over n. So here's what I'd write for the height. The height is going to be the function evaluated at the right endpoint. So raised to the 2 plus 3i over n. And what are we going to use for the width? 3 over n. Okay? There it is right there. Okay, watch please. I mentioned this to you last time, but you need to be good at picking this out. That's where we start. That's the start of the interval. We start at 2. You're going to be able to see that in the evaluation point. So 2 is where we start evaluating. This right here, the number over n, is how long the interval is. Because remember, it's always b minus a over n, the length of the interval divided by n. So the interval's 3 units long. So where did we start? 2. How long is it? 3. So where did we stop? Stopped at 5. Okay, let's take a look at this one right here. So let's figure out, and I'm going to change colors, what's delta x? Isn't it 8 over n? X sub I, isn't it 1 plus 8i over n? Are we getting quicker at this? Okay, so this signed area, this net area would be the limit as n approaches infinity, sum from I equals 1 to n, big square root for a function value, and then I'm going to have a width over here. So I've got a height here, and I've got a width here. Height is going to be, here's my evaluation point, 1 plus 8i over n times my width, 8 over n. And again, you can look at it, you can see the height, you can see the width. Can you see where the interval started? 1. How long was it? So it must have been the definite integral from 1 to 9 of the square root function, because there you can see this, the function itself. Any questions? Okay. Let's look real quickly at this, and then we'll be able to get through the rest of the stuff tomorrow. You have some problems like this on your assignment. It says, find the following definite integrals by interpreting them as areas. I'm hoping that looks familiar to someone. It's the top half of a circle. It's the top half of a circle centered at the origin whose radius is 2. So it looks like this. Now, it really wouldn't be that much fun to go through and slice this up, but this is a nice geometric shape. It's a half circle. What's the formula for the area of a circle? Seriously?
R squared.
Pi r squared. Okay. What's the radius on this circle? 2. So this would be 2 squared. Okay. And then I'd have to divide that by 2. So the answer on this one is 2 pi. Now, we don't have to worry about it being negative or signed area or anything like that, because that's entirely above the x-axis. Let's look at this one, because we're going to use this a couple times. Net area, signed area between -1 and +3 for the function 2t. There's the height. That tells us the height. Tells us we're integrating or accumulating area with respect to t. So this goes through the origin and has a slope of 2. So it looks something like this. If this is -1, there's 1, 2, and 3. So there's the area that I'm after right there. If I'm integrating from left to right, from -1 to +3, what would this count as? Okay, so that signed area would count as negative. How wide is it? It's just a triangle, right? 1 unit wide, 2 units tall, so that would count as -1. This is 3 units wide, and how tall would it be? 6. So 1/2 base times height, that would be +9. Okay, so this is a signed area. This is a signed area. What's the answer to the problem? Answer to the problem is the net area of +8. Okay, and one last one and we'll be done. I want you to look at that for a second. Trig wasn't that long ago. Think about what that would look like.
It'd be 0.
Weston says 0. Okay, if we're integrating from -pi to pi, we're integrating it in a positive direction. Anything below is going to count as negative. Anything above is going to count as positive. What do we know about these two shapes right here? Not what area, but they are the same, and one of them is below the x-axis, one of them is above the x-axis. They would cancel each other out. The net area would be 0. Okay? Any questions? Okay, that's enough for now. We'll finish this up tomorrow. Please make